Yes, sir, you're
Yes,
audible.
sir.
Slide is visible, right?
Yes, sir.
So far we have discussed the basic idea, that is basic introduction of robotics, and we have discussed related to the fundamental topics we have discussed. Now we are going to see the research trends in robotics. Why I am specifically showing some of the slides may not be in detail. Those who are interested in detail, they can contact directly. But even though some idea I will try to give you, and I think this will motivate you to come up with some ideas to do research on this area of robotics. Now, the research started long back, but notable research was started in the mid-70s in indoor wheeled and static block world. That means generally in mobile robot, in wheeled robot and manipulators started the classical AI robotics in around mid-70s, and mainly based on the methodology of sense act play. The robot will sense the environment and plan accordingly. You have to go for, robot has to go for planning, then act. And there will be a complex world model and reasoning, then maybe a mathematical modeling, or maybe some other modeling with the environment. That may be a local based modeling or world based modeling can be, or used that time. And after that, in around 80s, there was no model. World is a model. That means I can say in another thing, in the optimization and all, when we are going for optimization, there may be a local optimization, global optimization, or maybe a world is a model. There will be a specific model, and it will go for either, these technologies are implemented in static leg motion. While robot is walking, static walking has been, implemented. In leg motion, while we are walking, there are different kinds of stability, static stability and dynamic stability, or pure dynamic stability. But it implemented only static stability, or we can say quasi-static stability. Static stability means when we are standing. Suppose when you are lifting one leg, then system will be stable, right? So only that static kind of leg motion has been introduced during 1980s, and some robotics have introduced, and simple sense act functions also integrated along with this in around 80s. And in 90s, models at higher level, that is, there's a complex models have been introduced, and complex control algorithms have been introduced around 1980s. That is, sorry, in 1990s. And in complex environment and mapping, localization, and human-robot interactions are introduced. The topics were introduced that time. And in around mid 90s, around 2000 or 90 to 2000 range, dynamic leg motion, that is, as I said earlier, when a human is walking, there are different modes of walking: static walking, dynamic walking, pure dynamic walking, etc. And dynamic leg motion were implemented around that time. And water vehicle, that is aerial and underwater vehicles, have developed much during this time. There are a lot of research in planning, implementing in these areas had been introduced or implemented in during that time based on the probabilistic models. And now after that, there are a lot of research in the kinematic parallel robotics, and as I said, some of the research topics we are going to see. And what are the research topics happening in this time, during this time, and all we'll discuss. These are the old technologies and new technology and new topics we are going to discuss now. And current research include cooperation, coordination, robotics, actuator sensors, actuator development, intelligent robotics, etc. Some of the areas. We'll see one by one. I'm going to give you a basic idea, not in detail. And one of the important topics, those who are in electronics or electrical background, they can do much on this than the mechanical people. But this is purely related to the optimization and communication. Then swarm robotics, you know what is swarm robotics? A number of robots will be there, and a number of robots will communicate each other, and at least one robot. Suppose you are making a swarm robots of 10 robots, small robots, and these 10 robots, at least one robot will do one objective. Suppose you are hitting a person or hitting a target. I will be sending 10 robots, and in between some robots are having some issue and some robots are not working. Then suppose 10 robots we are sending, after some time 5 robots have been some issue and it's not working, and remaining 5 will communicate each other, at least one will do the operation. So in US, NASA and US, some of the universities have implemented this kind of some robotics. Land itself, land robots. So land swarm robot means wheel robot or tractor or any robot, small robot, thousands or hundreds of robots are communicating each other. At least one robot will do our goal, objective. And in underwater, again, underwater also you can do it. In water also you can be aerial robots and aerial robot, 100 robots and communicate each other will do some target. Target isn't reaching the target or hitting the target or maybe achieving some particular goal. And that is coming in the some robotics. And mainly the technology coming in this is optimization kind of thing and communication between the robot. So that is some robotics. You can say robots, and you have a communication and coordination between these robots. Then this is swarm robots. Number of robots will send, and at least one or 2 robots will do the final objective or implement the final objective. That is swarm intelligence, swarm robotics. And another, the inspired by biological collective systems, the flexibility and adaptability, enhanced task performance, higher reliability, distributed sensing, and low unit complexity, then decreased cost over traditional robotics. These are the important features of swarm robotics. This is one area which those who are interested in electronics or electrical background, mainly electronics background, they can focus on this area. There are a lot of scope for doing this research, mainly aerial. No, you can do land, you can do underwater, you can do aerial, or you can hybrid. You can do aerial with land, underwater or water, and you can integrate hybrid form of collective form of swarm robotics also can be done in this area. So that's one area, important area. Another, see, these applications very important. Space crafts, inspection, maintenance, surveillance, search, rescue, chemical source tracing, mine detection, construction, agriculture, and medical robotics, medicine robotics. This is one area. Another area is dual robot. For example, we have 2 arms, right? And generally you can see robot manipulators with 1 arm. And if you are having 2 arm, there are a lot of dual, we'll call it a dual arm. Why dual arm? Where 2 arms, right? Robots are having 2 arms. And these 2 arms can be used for coordinated work. As we are doing, these robots can be done for assembly operation or some coordinated task between this hand. So that is another important research area. And these are the cameras you can implement. Maybe with 1 camera also you can implement. But a human-like arms to ensure safety and body with the integrated controller, collaboration with the human worker. This robot will be collaborating with the human worker. Productivity and flexibility is high, lightweight, easy to mount, agile motion, the cycle time, and the same for parts assembly. This is another mode of robot, another type of robot. You can do either you can develop a dual arm robot or you can do the different coordinations. Even for example, you take a very accurate operations, very what is a specialized operations also can be done. You take a needle and thread. If you are able to move through the needle hole, it'll be very interesting. It's very difficult to do that kind of operations. If this robot is doing that operation, you can see these are, you can say this is a higher level of work. Because we know that how human is doing, robot is not able to do achieve even 5% of work as human is doing. So there are a lot of scope in this area to do to achieve the human-like operations. Now this is another kind of dual arm robot. You can see the camera, and these are the dual arm, and fast speed, precision, and packaging, loading, and machine loading, material handling, etc. can be used. This kind of robot. Then another important area is a wearable robot. Wearable robot is, generally you can see, we'll call it a robot exosuit. And these robots will helps the, for example, this kind of exosuit or this wearable robots are implemented in US in military. And suppose our efficiency after after traveling that much distance, maybe at difficult terrains, the soldiers will be weak, muscles will be weakened, and those problems can be overcome by using this kind of a wearable robots. Wearable robots will be, what I say, improving, enhancing the, what I say, the efficiency of the soldiers or human whenever required. Suppose the efficiency gone decreasing to 70, even with increasing to 50%, the efficiency can be more than one also, that is 100% also. And that is known as a wearable robot. Robot exosuit called soft robots are for military and medical applications. And robot fabric for very active closing and embedded. Maybe another thing is smart shirt, a smart shirt you can, you have seen, you have heard of smart shirt. Depending on the climate and all, robot soldiers are using sometimes this kind of, in US and other using this kind of shirts, smart shirts that can be used for what I say, the closed loop control of the climatic conditions, temperature of the body based on the climate and the body temperature. Will do a closed loop operations, and finally the person who is using this smart shirt will be comfortable. Okay. Now, see, this is another area, parallel robot, pick and place operations, parallel kinematics, parallel dynamics, parallel control are very important, because when we see the serial manipulator, this flexibility and accuracy will be higher. And but only problem with the large payload capacity, higher repeatability, impressive works. One important problem is the larger workspace. We won't get the much larger space as compared to the serial manipulator. But the flexibility, stiffness, and all will be higher for this particular type of robot. Another area of parallel robotics, another area, another area is the prosthetic. Lot of research is going on in this area. Many prosthetic hand have been materialized, still under development. And mind-controlled modular prosthetic hand. See, there may be EG, EMG control and all. And based on that, the robot hand can be controlled based on our requirement. I mean, for our satisfying our requirement. Suppose we'll think to see, pick an object or taking a glass of water and for drinking, and the signals will be analyzed by the EEG and EMG, EAG integration. Then the required operations can be done, implemented by using EEG cap or EMG, EEG and EMG integrations. And that is another area, but there are a lot of algorithms that to be tested and improved for getting improved version of the motion or increasing the accuracy and speed. And few achievements in the field of APS, modular prosthetic link, and which senses the motion-based pattern recognition, not only gives control over limb movement, but also touch sensing. This is another area because you can develop a mechanism and you can develop a mechanism and you can integrate the various sensors. And you can integrate EMG, EEG to implement some vertical motions. And for example, another thing is if you are very simple project, if you are having a 2 degrees of freedom hand, as a faculty, if you want to teach, you can make a teaching robot. Okay, you can make a teaching robot. You can design a 2 degrees of freedom robot, and it's a planar robot. You can fix on the board and you can do it. Either you can sense, integrate with the vision sensor, or maybe you can add the artificial intelligence, or you can integrate with your EMG with that robot, EMG and EEG combinations to that robot, and finally robot will do the operation which we are going to deliver some maybe lecture that can be done implemented in robot. These are some idea you think of. These problem can be given to the students, and that may not be easy. That may be a research problem also. Okay, that how what are the ways which you can do it. You are going to do it, and all very important. For example, you have 2 degrees of freedom robot. If you are designing a teaching robot, you based on the vision, you can make a single teaching robot, and you can make an intelligent robot for teaching, and you can integrate EEG, EMG to that robot. Suppose you are going to teach, you are a teacher, you are going to implement, that can be implemented with a robot. That's another research topic, research problem. I am posing some research problem that can be, you can take care of you, and you can give to your students also, or maybe you can also proceed. And this is unmanned aerial vehicle. This is what I told you. There are some drones, nano drones, aerial photography and video recording, and agriculture, agribotics, process agriculture for doing the process agriculture, and for aerial robots, self-driving car, unmanned drones, unmanned spacecraft, driverless train, driverless car. Okay, so these are driver assistive car. All these are some of the important areas. Those who are related in image processing, vision, and computer science students, I mean faculty and students, and even electronic students can focus on this, because they are having much idea sometimes than mechanical. So this area can be is very much useful for computer science, and mechanical design the mechanical students can do, and you can make a team and you can do it. Because if you are very important issue, I mean very one of the important uh, method or shortcut to develop the knowledge is, you instead of going for departmentalization, you take an interest in some students from electrical, electronics, computer science, or other branches of engineering including mechanical, and you can form a group and you can give some project, and all these stuff, their own stuff, you can add it and they can develop a lot of things. So you make a group, and that will be helping for come up with new ideas, innovative products. Generally, I am doing that because we have a robotics interest group in an ATAL Academy, and we are developing a lot of things because we have students from even from not only from engineering, from science, physics, chemistry, all students are there, and they are contributing their own ideas, so that we can integrate. Even biotechnology students are there. A lot of things can be developed if you're doing like that. So you try to make a group so that it will be useful for you. You can learn it. You can develop new things, new innovative products. So that is unmanned aerial vehicle. And again, as I said, the swarm robotics can be implemented. You develop new system, and you can 2-3 instead of one, you take 2 or 3. You can implement a small swarm robotic system. Instead of going 10 or 15 or 20 or 100, you can go for 1 or 2 or 3 with a very high-end robot. That will be fine. Initially, when you are going for swarm robotics, you try to implement with 2 or 3 initially, then you increase the number. Like that, you have to develop. And another area is nanorobotics, but in India, nanorobotics is not there. And you can see there is a lot of universities abroad are doing nanorobotics. It's emerging technology, potential applications in nanomedicine, targeted drug administration, will be used for cancer and diagnosis and treatment of diseases, special cancer, uses on organic tissues like dissection of hepatitis C virus has been already been tested. And you see robots are tubular. Robots are tubular, about 20 microns long and 2 microns in diameter, and coated in zinc. And see here, a micro motor powered whenever robots have been delivered, and nanoparticles compound directly injected to the tissue of live mouse. So this is what I told is tested in the mouse. So a lot of scope in the simulation and implementation work in this, but we cannot do it in India, and we have to go for this kind of research in special type of universities. And another is medical robots. You can go for surgery. Surgical robot is another area. You can develop a surgery. You can go for a master and slave mechanism. You have a master and you have a slave, and slave is doing exactly the surgery, and master will be in the room, and doctors are controlling this master so that uh, uh, the same motion can be incorporated or in slaves, and that can be used for doing some surgical operations. Now this is robot assistive technology, and robot assistive technology, there are a lot of, even though there are a lot of mechanisms developed, but real implementing part is missing. Real implementing part is missing, and real output is missing. So there are a lot of things can be integrated in the assistive devices. And you know, the another important area is agriculture robot. I have added because of the request this agriculture robotics. You know, there are in agriculture robot sowing the seeds, plantation, watering. These are some requirements, and all these requirements we can use agriculture. For example, I'll show you one project done by one of my students. I think I'll try to project that. I'll share that PPT. See, these are the, I can see in agriculture robot, you know, the agriculture robot machinery instead of traditional manpower had become a major trend in the world of farming. And multifunction farming robot is now an important target in the research development of agriculture. There are lots of research going on in the development of the developed countries. Hence, research is, the technology is high, and we compare with India with the developed countries. So these are some of the robots for agriculture, and see here, agriculture robot research is conducted the following agriculture activities. So before going for this kind of research in this area, you should know what are the requirements. Okay, the following agriculture robot research is conducted for what? Harvesting, you can use it. Precision seeding, you can use it. Weed removal, you can use it. Fertilizing, watering of plant, spraying pesticides, you know, fertilizing, spraying. Even the aerial robots are using now in almost even India also for watering and spraying pesticides, picking, harvesting, and seed mapping and reseeding, plant health monitoring. The robots can be used. See, so these are some of the requirements of robots in agriculture. And see the need for agriculture, the need of agriculture robotics. See precision seeding, how precisely you can seed. Sometimes if the seeding is not proper, it will be an issue for the plant. So sometimes it won't grow also. Now, precise fertilization, reduce fuel consumption and air pollution, reduce need of human intervention, problem of absence of workers, decreasing number of farmers, increasing environmental impact of food production can be addressed. So these are some of the need for agriculture robots. And you see here, what was what we have done is we have done a conceptual design for what was the objective was the design, fabricate, and experiment multifunction robot for row crops in Indian conditions. Indian conditions, so row crops, how we can implement for planning for row crops. And the same robots can be used for harvesting also if you are adding some of the other kind of mechanisms, plucking mechanism or some other mechanism. If you are adding, the same mechanism can be used for that also. But the problem is this robot can be used for flat terrain kind of thing, marshy field and all. We can additionally add some mechanism in the ground, in the bottom, and we can be used. That also we have developed. But if you are going for other kind of wheel mechanism on marshy field, that can be improved. Only thing is that bottom portion can be improved. And another thing is, you see, this is the seed feeding mechanism. You have seed bin and feeding to the mechanism, and whenever while it's moving with the uniform speed, and digging and feeding will be is done by this particular robot. So this is a robot we have fabricated and we have tested, and this is a wheelbase, and we have tested, and we have implemented the steering. So this is another one kind of robot. Then another kind of robot is see. Stop sharing. Okay. So another important type what you can do is you can go for another important issue with some of the poultry farms. It's very difficult to clean the poultry farms. So you can go for developing the poultry farm. We have developed a poultry farm robot. I'm not having that slide. And we have developed a robot for watering the plants and spraying pesticides and weeding. All those things can be done for agriculture. And also the harvesting. Harvest is another, depending upon the type of
So sorry, can you please enlarge the screen?
so depending upon our requirement, harvesting, which type of crops or which type of item you have to harvest. So based on that, you have to change our gripper, robot and defector and all. That is that itself another research topic. Developing and defector itself another topic for what I say the for harvesting. And so first thing what you have to do is what is our objective? The objective should be clear. For that, how many degrees of freedom? You have to go for design, then you have to go for control. First you have to design the controller, you have to fabricate it, control implementation and fine tuning, then what I say testing, then again sometimes you have to improve, finally you will be getting a final product. Like that you have to develop the product. And now I'm just this old slide, new slides, I couldn't include some of the figure. And these are the robots activities and ATAL Academy. I have developed some of the robots. I'll show you some robots. And this is, we have developed a lot of serial, parallel, hybrid manipulators. Serial manipulator, parallel manipulator, and hybrid manipulators we have discussed. We have developed. And another important area is parallel kinematic machines. Parallel kinematic machine is development of parallel robot. Parallel robot. And these parallel robots, if you are using for some machining operation, we will call it as parallel kinematic machines, PKM. So parallel kinematic mechanism, if you are using for the machining operation, we will call it as parallel kinematic machine. That is very important research area. We have developed parallel kinematic machines for various applications. So drilling, milling, and also so for what I say another parallel kinematic machines, that is 4PRR 4P. That is 2P means, it's a hybrid manipulator. 2P means you have the base. 2P prismatic. 4PRR means 4 legs are there. Prismatic is the 2 revolute. That is what? 4PRR, 4 legs. In each leg you have PRR and 2P is the serial. So this is a hybrid mechanism. And this hybrid mechanism is used for water jet cutting. So water jet cutting, we have developed this particular mechanism. And another important is the dual arm parallel robot. This is one arm, this is one parallel arm, this is another parallel arm. As you saw a dual arm robot, but both arms are serial. But here both arms are parallel. This is parallel manipulator, this is another parallel manipulator, but you have 2 arms, and these 2 arms can be used for doing some coordinated task. This is dual arm parallel robot. And again, you have 3 PSS, that is 6 PM. Prismatic, spherical. That is 3 legs, 1, 2, 3, and 3 legs horizontal. You can say 6 PSS also. And this is another kind of robot. One of my PhD scholar is doing this for scanning operations. So you can go for scanning operation, because the end effector, if you are this kind of mechanism, if you are adding end effector, it won't be a force resistant, the mechanism will change. Although in non-contact applications, we are developing this particular mechanism, 6 degrees of freedom mechanism. And another, this is the row crops, as told you. This is a humanoid robot, bipedal robot. My specific area is humanoid robotics. I have done the research in humanoid robotics. And in humanoid robotics, what I did is, in the literature, in the recent literature, the slide on research, yes, I told you first is leg locomotion, second is first is static, only for standing, and next is dynamic walking. But what I did is pure dynamic walking. That means you have to reduce the size of the foot to a point so that any kind of terrain you can walk, you can locomote, you can move. So that is my research area. So one of my MTech student, our PhD student, is doing developing a humanoid robot, bipedal robot. This is the structure. This is not completed. This is on the way. And these are the mechanism, humanoid robot. And these robot, after developing, you can train the mechanism. You can make it an intelligent also if you want. So there are a lot of scope in this area. If you're having a hardware, lot of things can be done. And this is the kinematic model of this particular robot. And we have simulated also. Simulated walking and step climbing, all can simulated work, and we have modeled also. We have developed also. And we have had a small robot. We have developed a small robot, and we have tested in a small robot this kind of motion. But this robot is different. This robot is of over height. It's coming around, 1.5 meter height. But this is a small robot we have developed, and we have tested in that. So then another is overhead transmission line. One of my PhD scholar completed this transmission line inspection development of transmission line inspection robot. And we have tested, we have made a setup in the lab, but online we couldn't do because there are some ethical companies that we need testing facilities and all. We couldn't do, but the mechanism is ready for testing. And we have developed a mechanism and online inspection of electrical line, the suspension line, or had the high voltage transmission lines, those, electrical faculty or electrical students know about the significance of that. What are the difficulties in crossing the tower? You have the jumper cable and all. Through the jumper cable it has to move. So it's very difficult to develop a transmission line inspection robot. So we have developed 2, 3, 4 designs we have tried, and finally we have implemented in one mechanism, and one student has been completed PhD also in this area. In another robot is humanoid upper part, not lower part, upper part, the wheel base, and one of the student, my PhD student, is doing development of this robot in this area. And another is cleaning robot. Cleaning robot, there are a lot of world cleaning robot in the sense, control river cleaning robot, river cleaning. So pollution is one of the important issue, and we have developed a robot for cleaning the river. And this is a testing setup, and we have tested in the pool, swimming pool of NIT Calicut, and we have cleaned some of the plastic waste and we have cleaned from the river, and we have developed and we have implemented that in the river, and higher level of depth control and all we are doing on this, and we have participated in the competition. We got a prize also in Singapore, and this is one of the important hardware we have developed in NIT Calicut, and again higher end research is going on in this, and this is developed by BTech students. Now see this plastic weights and it's move and that, but underwater it's moving. There's some issue that has been solved, and depth control is done well now. Now this is another PhD student. He's doing this started with one BTech students table tennis. Tennis playing robot, and this tennis playing robot same control and identification is doing by one of my PhD scholar, and he is doing after modification of this mechanism. This is not the mechanism. This mechanism is developed by BTech students. And see these lot of students, as I said, we have a robotics interest group. Those students are doing, and all the students, about more than 70% of students, 60 to 70% of students are going abroad for higher studies yearly from the lab. And this robot has been modified, and testing now the implementation part is going on, and one of my PhD scholars is doing, and this is Our objective is to, after developing, we have to test with the the autism autism people, autism disorder spectrum disorder people can be affected, people can be tested, and how the performance can be improved. Sometimes the autism people, research says that this kind of, not by using this kind of robot, other robots are using, human robots are using for autism robot or autism people to improve their capabilities, communication and all. This also can be used. Our objective, our expectation is we can do much by using this kind of robot for the autism people. And this is another area. And another is, generally, the adjustable bed. This is a patented bed. The bed, generally in the hospital bed, we can move in like this fashion, but this can be rotated in any order, or in sagittal plane as well as the frontal plane, and height can be adjusted, and all those things can be done. But now students are started to develop a system. You can also try how there's a lot of, even I am in our what I say, TNP, that center, and we are getting a lot of research proposal from outside, and we are sanctioning some fund also for patient transferring system, patient transferring system, will wheelchair to this, or mechanism from another system to the bed. Okay, patient transferring system, that also take care. And you search it, patient transferring system, you will get an idea. If you're having a very good idea, there are a lot of scope for starting the going for startups. So we are funding that, and ATAL is funding for this kind of proposals. And another special kind of wheelchair, I think IIT has developed a wheelchair. This can be stand and sit, but slightly long back itself we have started that, and we have modified, and we have somewhat we achieved, and some more work is remaining, but the functionalities are different. I'm not going to say that now. And this is exoskeleton we have developed for physiotherapy for the hand motions. And this is a wearable assistive device for deaf. And these are swarm robots we have implemented in Firebird. By 3 or 5 robots we have implemented. And quadcopter we have developed, and we have used for various applications for in agriculture. And this is another important area. And this is also a finger reader for blind. That's another area. These are all I'm just showing. The shortage of time, I'm just showing this. You can also focus. You can read it. No, this is for the blind. Finger reader for blind. And this is a shop board. See this, sorry. This is a shop board, because if you are giving some, you'll have a database. You can enter the item which you want, and robot will go and pick the object and will come back. So this has been implemented in our library, and other, this can be used for the shops also. That is why it's known as a shop robot. So then autonomous book retrieval robot is another robot which I have discussed, developed. And this robot there are some issues with this robot, but it was implemented fine. And what we have done is we have a database. We'll enter the book name, and robot will go and pick the robot and will come back. But the problem is, this is a line following robot. The issue with this, that much space and some issues are there. But instead of that, you think of maybe overhanging from the top. Maybe you'll have just like your 2 hands. This is overhanging at the top. Then it will be moving the top, and you can pick and place it. That also you think of. You can. These are some work. These are some problem I am posing you. You can try that. This is only a land moving robot because of based on line, and this can be changed to a overhanging one. We thought of doing, but we didn't start that work. Then these are the identifying and picking the object, and it will come back. Design development autonomous transmission and inspection robot, that already I have told you some of the issues. These are the robots we have tested, and this is the robot. These are robots. So these are the things related to the work we have done in the robotics lab. Then we'll move to the, because of shortage of time, I'm moving fast. I mean, slides are moved fast. So I think you got some idea which are the work we are going in the lab, and you got some idea that what are the things you can do with your students, or you can do with your own. I try to give you some of the idea and what are things we are doing in my lab. Okay, with this we'll stop the first part, and we'll start the next session, that is the robot manipulated dynamics of manipulator. So if you're having any queries related to this, you can ask for 2-3 minutes. You can ask, because to start the manipulation. If you're having any doubt, you can ask any questions.
Participants can either unmute yourselves to ask the doubts, or you can use the chat option. I'll read out the questions.
All questions?
Chair, I think there are no questions.
Okay, we'll move to the next. Okay.
There are just few comments like nice and interesting, but no questions are being posted.
Okay. Okay, so we'll move to the next manipulator dynamics. See, so far what you have done is just a theory. But now we are moving to the modeling. See, I think the audience are not only from mechanical, all other, I think mostly from electrical, right? Okay, so you should have an
Yes,
idea.
sir.
Is it?
Sir, I just in that chat. Could you please share about the electrical transmission line inspection robot papers? Where are they published?
Hello?
Sir, I was audible? I just read out the question from the chat box.
Yeah.
Yeah, Dr. Srikanth is asking about the electrical transmission line inspection robot papers. The papers related to that particular robot, where are they published?
So one thing is we have sent for patent. The patent has been published. Okay, patent has been published. If you want, you can share this one. That's number one. Then another thing is we have published 3 papers and 2 book chapters and 1 book chapter and some conference papers. All these papers you can search directly. You will get it. One we have published in, one is Industry Robot, another is Brazilian Journal, another is Simulation Modeling. These 3 journals we have published. If you want, I can share the copy. You can mail me. I'll share the copy. Okay.
Thank you, sir.
Yeah. So I think I'll give you my email ID. I can share you this one. Okay.
Thank you very much.
Okay. So anything else? But the thing is, complete mechanism is not open because we have gone for patent. But some idea, most of the idea will get it. What are the technology we have used and all.
Okay, sir. Thank you.
Okay, we'll start, Akila. We'll start, right? Can
yes,
we start?
Sir.
Okay.
Yes, sir, we can start.
Okay, so now I think the audience are mostly from electrical. Akila?
Yes, sir.
Audience are from only electrical department or from various branches?
So we are having from various branches.
Okay. Okay, so you know, kinematics and dynamics The kinematics and dynamics, we are all studied even in engineering mechanics, the first year. That subject is sufficient to learn mathematical modeling. If you are having the idea of engineering mechanics, that is sufficient to learn the modeling. So the kinematics and all, I think kinematics will be covered maybe within 1 or 2 days by other expert. And in the kinematic, is just like a position analysis. We are focused only on motion study. We are not focusing on forces acting on the system. But in manipulated dynamics, we have to focus on the force and torque acting on the system. So in the manipulated dynamics, I'm not going to discuss the kinematics, but see what is the significance of mathematical modeling in robotics. One is the kinematic modeling is very important for design. Design in the sense you have to get the workspace, you have to get the dimensions for link, etc. Then static and dynamic analysis. I'm going to focus only on dynamic analysis. Dynamic analysis is very important for selecting the actuators and minimizing the energy, and also for control design. Those who are in electrical, they'll get idea. If you're having a dynamic model, mathematical model, then only you can do the dynamic controller design. So you can design a dynamic controller, or you can design a controller if you're having a dynamic model, mathematical model. But if you are not knowing the dynamic model, the issue is you can take it from the paper and you can do the modeling. But at least you should have a clear idea about the dynamic model. Otherwise, what will happen is, I'll give you an example. Even in ATAL Academy itself, I was generally, we are going for Viva, maybe PG Viva and all. Even MTech as a DC member, what I have seen is some of the people are designing a controller by using dynamic model of the system. But the dynamic model they are taking from, sometimes they are taking from some other literature, research papers. But if you're taking the research papers or literature, the issue is, instead of theta, if you are some theta, instead of theta dot, if theta is there, theta dot is missing instead of theta, or theta dot is coming instead of theta, the complete model will be failed, or complete controller will be failed. The dynamic behavior cannot learn also. So that is the issue with that. If you are knowing the model, you can make a mathematical model and you can make your own controller. See, another thing, if you want to design a robot, you have to design the robot. You have to, kinematic model is required, and if you're having a dynamic model, you can design a controller for that, and that specific controller you can implement on that hardware. That's the advantage of the dynamic model. So the dynamic model can be used for the control design, or the dynamic behavior of the manipulator consists of set of equation or model.
Sir? So you're not audible. Participants are please requested to wait. I think maybe sir is having some network issues.
Hello, am I audible?
Yes, sir,
Audible?
you're audible. Yes, sir,
Okay.
audible.
So sorry, there is some internet connectivity issue. Okay. So I'll
But
share
the
that.
screen is not visible.
Yeah. I'll share. Okay. Now it's visible.
Yes, sir. But full screen and full screen, please. Yes, sir. Fine.
Now, we were discussing about the importance of dynamic equation or dynamic model, and force torque can be identified. See, as I said, if you want to rotate it, suppose you have three link robot, you have to, after making the mechanism, after manufacturing mechanism, you have to fix the actuator, electrical actuator, different joints. If you want to fix the electrical actuator, you have to select the actuator. If you want to select the actuator, you should have a clear idea, some idea about the what is the torque requirement of this motor. Okay. Now, how will you get that? By the dynamic model, mathematical analysis only. You will get an idea how much will be that, what will be the range. Suppose if you are not doing that, what will be the issue? You can purchase a robot, actuator, you can fix it. But if you're testing, sometimes it won't work. Again, you take the another actuator, you try it. Those like that, by trial and error, you can select the actuator. That is not the scientific method to select the actuator. For that, you have to model the robot mathematically, that is dynamically, and you will have a torque equation. You have to find out the torque for particular different operations. You plot it, and what is the maximum torque you have to find out. After find the maximum torque, you have to put some safety factor 1.5 or depending upon the mechanism, complexity of the mechanism, you put some safety factor. Then you will get a theoretical torque from the model, theoretical torque from the model, or theoretical torque from the plot. And the actual torque you will get after assuming the safety factor. So actual torque tau A is equal to 1.5 times tau T. Tau is the theoretical torque. Tau T is the theoretical. That you will be getting from the graph. And that into the safety factor, you will get the actual torque. If you are knowing the actual torque, you take the data sheet of the motor and you can select the actuator. That should be the methodology you have to follow. You have to teach your students like that to select the actuator. Okay, now dynamic actuator can be used for the energy calculation. I'll tell you, suppose when you are doing some operation by using your hand, for example, you are eating something. You are eating something. If you are eating or drinking something, your hand is moving in a particular fashion so that the joint usage will be minimum, energy usage will be minimum. These calculations are already, doing by your neurons. Neurons will calculate the path or the how this your hand has to move to do some operations or eating or some other operation. While eating, we are doing like this. We are not doing like this, right? Why? There will be strain. So all these calculations, power consumption, are calculated by our neurons. Same way, you can calculate what energy utilization for the robot by if you are having the dynamic model. So if you are having the dynamic model, what is the power requirement of robot? What you can do? You move through different trajectory, and each trajectory, what is the dynamics? What is the torque requirement? What is the energy usage? And you find out thousands of trajectory, which is a minimum trajectory that you can use it for doing some operations. And that is a methodology you have to use for energy or power optimization. So these are the advantages of dynamic.
Sorry for the interruption. There is
Yes.
a question. Please mention the softwares that can be used to dynamically model the robot manipulator.
So see, there are some mechanisms. The problem is this software, because if you want to do a 3 degrees of freedom or 4 degrees of freedom robot, you are going to design based on your own requirement. That's it. So you can make it, but what is happening in that? What is the torque requirement? Just for identifying the torque requirement, you can model it and you can use software. Adams, you can use it. Adams is a software. Adams software, you can use it for finding the torque and force requirement, Adams. And there are some IIT Delhi developed a mechanized software, that is robot analyzer. Mecha analyzer is there for identifying the torque and all. But that is not full-fledged. But Adam is a very good software for finding the torque. But you can find out torque only. But how can you identify the energy? If you want to minimize the energy, for example, if you want to move your hand, as I said earlier, if you are eating something, you can move through a shortest path or maybe with minimum energy path with minimum utilization of joints. How can you do that? Only with Adams, you can find out the torque only. You cannot find out the power also. You can find out the power. But the problem, if you're having a mathematical model, you know the angular velocity, you know the torque, and you can find out the power requirement of rotor power. So what you can do, you take thousands of trajectory, And through trajectory, each trajectory you find out the power requirement, which is the minimum power used in the particular trajectory. That trajectory you have to use for doing some operations. So that's a methodology, you can use it. But if you are using the software, there are some limitations. You won't get complete idea. That is the importance of this modeling. So if you are doing as 2 degrees of freedom or 3 degrees of freedom by your own design, that can be modeled, and you can find out the torque in atoms and all, but you cannot minimize the energy and all. And you cannot design a controller because you are not having the mathematical model. How can you design a controller then? So just for identifying the torque and all, you can go for this software, fine. But software will help you to check whether your mathematical model is correct or not. But actual control design and minimum energy optimization, you have to do the modeling, which we are going to discuss. It's not a difficult job, but simple model you try first, then complex model after that you can do it. So these are the advantages of a dynamic model. But you should know why we are going for dynamic model. We can go for software also. We can go for software, but you won't get complete idea of that. Yes. Yes. Hello? Okay. So then next is there are 2 types of approaches. One is Lagrangian-Euler-Lagrangian formulation, and next is Newton-Euler formulation. The dynamic, if you want to do the dynamic model, you have 2 more types of modeling approach. One is Lagrangian model, other is Newton-Euler formulation. And Lagrangian-Euler formulation, you are going to use the energy-based approach. So energy-based approach is a Lagrangian-Euler formulation, and take into account of each link you consider, and you find out the kinematic and potential energy of each link, and then you find out the torque. That is a Lagrangian approach by using the energy-based approach. It's very simple. I'll explain to you. And Newton-Euler formulation is the next approach. And this approach is useful if the degrees of freedom is very high. For example, in my case, I used in humanoid robot. So 12 degrees of freedom, 25 degrees of freedom and all, you have to use Newton-Euler formulation. Now, Lagrangian approach is very difficult if you're having more degrees of freedom. So I think more degrees of freedom, more than 6 or 5 or etc., you can go for Newton-Euler formulation. So low level problems, you can go for Lagrangian formulation. Low level in the sense degrees of freedom is less, you can go for Lagrangian formulation. Newton-Euler formulation can go if your degrees of freedom is higher. And that method, Newton-Euler formulation, is a force torque based approach. Force torque based approach. It employs force moment balance. Force and moment balance we are going to use in Newton-Euler formulation. So Newton-Euler formulation we are not going to discuss, but you try to understand these are the basic model. Other than this, there are some other dynamic models also, but these are the generally using method, Lagrangian Euler and Newton-Euler formulation. But now we are going to focus only on Lagrangian Euler formulation.
So we have a question on that. Which method is more suitable for 4-legged robot?
4-link robot, now see, one that is these 2 approaches are different approaches. But I can say Lagrangian model, 4 degrees of freedom and all, you can go for Lagrangian approach. Okay, Lagrangian approach. Newton-Euler formulation, the thing is, no, Lagrangian, Newton-Euler formulation, there are some approximations. But in Lagrangian Euler formulation, you are having 4 degrees of freedom and all. You can go up to, up to 4, 5, and you can go for Euler Lagrangian formulation. But sometimes some research paper you can see even at higher degrees of freedom, they have used Lagrangian approach by using some specific method. Lagrangian approach only, but they use some algorithm to program. So even Lagrangian approach is sufficient. Okay. Newton-Euler formulation also you can use it, but you are going to see only Lagrangian now, you can focus on Lagrangian. But if you are knowing both, I can say Lagrangian is better, but formulation is a little bit difficult for higher degrees of freedom. Up to 4, I think it's not any difficult job. I'll explain 1 or 2 degrees of freedom and all now, then you will get idea. Okay. Now, See, in Euler-Lagrangian formulation, you have to write the equation state space form. State space form. So torque equation you will get it mathematically. Then you have to write m theta theta double dot, p theta theta dot, and g theta. So m theta is a mass matrix, v theta is centrifugal Coriolis term, and g theta is a gravity term. So that means after forming the torque equation, you have to write in this form. We'll see what is a Lagrangian and Lagrangian approach. What you have to do is, first step is you have to identify the joints and link. How many joints, how many links, which is the type of joint, whether it's a prismatic joint or a reciprocating joint or maybe a revolute joint. That you have to identify number of links, number of degrees of freedom, number of joints, revolute or prismatic, that you identify. After identification, you have to find out the Lagrangian. Lagrangian is known as L. L is a Lagrangian. L is equal to K minus P. That is equation. L is equal to K minus P. So L Q Q dot means just L. K Q Q dot minus P P P Q. So Q is the joint variable. Joint variable means if you are having a prismatic joint, prismatic means reciprocating joint, you will say D is the prismatic motion. D, distance D. So you'll say Q, you can take it as D. So L, Q, D, D dot, if it is a prismatic joint. If it's a revolute joint, Q will be nothing but rotation, theta. So Q will be theta. So generally I have used Q. Q is either D or theta, depending upon the type of joint. Now K is a kinetic energy, P is a potential energy. So L is equal to K minus P is the equation. So Lagrangian you have to find out first. How can you find out Lagrangian? K is K minus P. K minus P. So suppose you have 2 degrees of freedom robot. For example, 1 degrees of freedom. L is equal to K1 minus P1. K1 means what? K1 is the kinetic energy of the first one link. Only you have one link. PA is the potential energy of first link. Suppose you have two links. K will be sigma Ki. Sigma Ki means K1 plus K2. So in 2 degrees of freedom robot, for the first link you will have kinetic energy, and second link also you have kinetic energy. So these two kinetic energy you have to add, K1 plus K2, that is K. And similarly, you will have potential energy for the first link and potential energy for the second link. So P1 plus P2. So the Lagrangian is K1 plus K2 minus P1 minus P2 in bracket. P1 plus P2. So the total kinetic energy you have to find out and total potential energy you have to find out. Then you have to find out the difference. Then that is Lagrangian. Once the Lagrangian is ready, torque you can find out by using this equation. D by dt into dou L by dou Q dot. Dou Q is the theta or D. Theta is for revolute joint, D for the prismatic joint. So dou L by dou Q dot and minus dou L by dou Q is the tau. Tau is nothing but d by dt of dou L by dou Q dot minus dou L by dou Q. That is equation for tau. So if you have a mechanism, to find out the dynamic equation or dynamic torque, first step is to find out the Lagrangian. How can you find out Lagrangian? Lagrangian is nothing but kinetic energy minus potential energy. And the kinetic energy is the sum of individual kinetic energy of the links. Potential energy is the sum of potential energy of individual links. So K1 plus K2 is K if you are having 2 degrees of freedom. P1 plus P2 is the P if you are having 2 degrees of freedom. If you are having 3 degrees of freedom, you have K1 plus K2 plus K3. For again K1 plus K2, K3, K4. Similarly, P1, P2, P3, P4, you have to find out sum and you have to find out difference. Then after getting the kinetic energy, Lagrangian, you have to find out the tau. How can you find out tau? D by T dt into dou L by dou Q dot minus dou L by dou Q. Only this equation you have to remember for finding the torque equation in the Lagrangian model. Now you see a planar 2 degrees of freedom. 1 degrees of freedom theta 1, here theta 2. Center of mass is this one. Center of mass is this one. You are assuming that this is a slender rod and with the mass is acting at the center of mass at a distance R1 from the joint. And this is the length L1, this is L2, and mass is M1 is the mass of the first link, M2 is the mass of the second link. Okay. Now this is X1, Y1 is the coordinate, and X2, Y2 is the coordinate of this P. Coordinate X1, 1 is the coordinate of this, X2, Y2 is the coordinate of this. Now, after that, what you'll do is you have to find out the kinetic energy of this. What is the equation for this Lagrangian? Anybody else? What is the equation for the Lagrangian for this particular equation for a particular system? Anybody else? You can unmute and say, what is the Lagrangian equation for this 2 degrees of freedom? Though here, the Lagrangian means you have kinetic energy for the first link, K1, kinetic energy for this second link, K2, because this is rotating about this second link, this is the first link. K1 for the first link and K2 for the second link. So K1 plus K2 is the Lagrangian. Sorry, kinetic energy, total kinetic energy. Similarly, at this point, what is the potential energy for the first link? At this point, what is the potential energy for the second link? So P1 plus P2 is the total potential energy. So K1 plus K2, right in bracket, minus right in bracket P1 minus P2, that is Lagrangian. So how will you get the kinetic energy? Kinetic energy of this first link is half mv square. You know half mv square. Mv is equal to r omega. This is r1 theta 1 dot, r1 theta 2. This is r2 theta 2 dot. Like that, you will get the kinetic energy half mv square and half I omega square about the rotational kinetic energy, and this is about the velocity based kinetic energy. Now this is I omega square. I is the inertia. Then after that, for K1 for the first link, you have K1, second link K2. So first link K1 is equal to half M1 V1 square, half I omega 1, I1 omega 1 square. So for this particular link, you have omega 1 R1, then K1 P1. So that's what you have seen, K1. So what is MV1? V1 is L1 theta 1. L1 by 2 theta 1. This is half. R1 is at the center means L1 by 2. L1 by 2 R theta 1 dot. So you will get L1 by 2 R theta 1 dot. So you will get, this is 4. 4 into 2, you will get 8 here. This equation 1 by 6 ml square is the rotation kinetic energy. Then finally potential energy is this one. So after getting the kinetic energy and potential energy for the first link, you have to find the kinetic energy and potential energy of second link. For that, to find the kinetic energy, you have to find out the velocity at this point. How will you get the velocity? You will get x2 and y2 are the positions. X2 dot is the velocity here. Y2 dot is the y direction velocity. So what is velocity at this point? Velocity at this point is root of x1 dot square plus y2 dot square. Now, how can you find out the velocity if you're knowing the position? You have to find out the derivative. So, x2 dot is the x component, y2 dot is the y component of velocity. If you are taking square root of x1 dot square to x2 dot square, you will get v2. So, x1 dot, x2 dot, you will get it. xy, you will get x2 what is x2? X2 is L1 cos theta, L1 cos theta 1 plus this one, half L2 by 2 cos theta 1. Similarly, y2 will get it. Then x2 dot, y2 dot, from this geometry will get x2 and y2. Then squaring and adding the velocities, then you will get velocity like this. And you know velocity, then half mv square you will get it. Half I omega square is you will get it for K2. And what is P2? P2 also you will get the same way. Potential energy is half mgh. Mgh is, no? Mgh is the energy, mgh. So based on that potential energy, you will get its equation, because you all know what is kinetic energy and potential energy. That's very basic, and only those equations you are going to use. After getting the potential energy, kinetic energy, you find out sum K1 plus K2 is the total kinetic energy. When P1 plus P2 is the total potential energy, you find out the difference, then you will get Lagrangian. After getting the Lagrangian, use this equation for finding the torque. If you are using tau, if you want to find out tau 1, first joint is, revolute joint is theta 1. So theta 1. So this is the fundamental equation. Low L is here. Differentiate it. And then again differentiate the respect to time. You will get tau 1 is this equation. tau 2 is this equation. After getting the tau 1, tau 2, you can write this as M, this as V, and this as G. Okay, then that is tau 1. Then tau 2 is again, this is M, this is V, and this is G. So you will get tau 1, tau 2. You can write in state space form M1, M2, M3. Sorry, this form you can write it. Okay, if you are having the model in this form, you can form the dynamic model, and this dynamic model can be used for the controller design. So you please, we have a 2 degree again prismatic joint. Here also what I have done is kinetic energy for this first link and second link we have found out. Potential energy for first link, second link you have found out. Then kinetic energy, potential energy difference you have found out Lagrangian. Then you use the fundamental equation. You will get the M theta, V theta, G theta. So you will get a torque equation like this. So this is the torque equation for state space model of mechanism. So here you have to find out M theta, V theta, G theta. For that, what you have to do? You have to find out the Lagrangian. Lagrangian is equal to what? K minus P. What is K? Sigma K I. Sigma Pi. You find out the difference.
Excuse me, sir.
Yes.
We have 10 more minutes to conclude the session.
I'll wind up now itself. Okay.
Okay, sir.
So now we have M theta, V theta, G theta. Then you will get tau. Then after getting the tau, you can use that particular model for the control design. So what I have tried to explain is, in the dynamic model, in the Lagrangian model, what you have to do is, you have to find out the kinetic energy of individual links, potential energy of the individual links. Then you find out some of the individual link kinetic energies and find out the potential energy of individual links, find out the difference, that is the Lagrangian. And L after getting L, you find out the torque by using the standard equation, that is this equation. Then you will get tau 1, tau or tau 1. Then after getting that, you change the theta values, you will get acceleration velocity change depending upon the time. Then you plot it, you will get torque variation. And after getting theoretical torque, you assume the safety factor. Then you find out the actual torque. Then that torque can be used for the selection of actuators. Okay. So these are the, then again, after getting tau 1, tau 2, state space model, you can use for the control design. So these are the points I have to tell you in the dynamic model. So in Lagrangian model, it's very easy. Only thing is kinetic energy and potential you find out all the links, add the kinetic energy terms, add the potential energy terms of individual links, find out the difference, you will get the Lagrangian. Then you use the standard equation for finding the torque. Then this is the standard equation for finding the torque. Then after finding the torque, you can plot it. You can find out the torque variation of different joints. Then you can use, you will get the theoretical torque. Then you can find out the actual torque by assuming the safety factor. Then you can select the actuators. And that model can be used for the torque controller design, And also, if you are knowing the tau, if you are knowing the angular velocity omega, you multiply tau 1 omega 1 is the power requirement of first joint. Tau 2 omega 2 is the power requirement of second joint. So you will get idea of the total power requirement of the mechanism for using for or doing some operations. So that also can be done, and you can use some algorithm to minimize energy. So these are the points I have to discuss related to the dynamics. Any questions related to this, please, you can ask in this.
So 2 questions have come up in the chat box. I'll read them one by one. So from Mr. Rohit, please explain Q again in the Lagrange equation.
Okay. See, this Q means now you are taking this mechanism. This is rotating. So here the joint variable is theta, right? Here theta 2, because these two are the revolute joint, rotating joint. But you see the next mechanism. Here this is rotating. So here joint variable is rotation. But here you see this is prismatic, moving up and down. So that variable is D2. So Q is a general term. If you are taking a revolute joint, that Q will be theta. If you are considering the second joint, then that Q will be D2. That is D1 or D2. That is reciprocal, distance move. So the Q will be theta or D depending on the type of joint. So if it is a revolute joint, theta will be, Q will be theta. And if it is a prismatic joint, Q will be D. For example, in this particular mechanism, if you want to find out the kinetic energy of this link, you have to consider Q as theta 1. And if you want to find out the force of this particular mechanism, here the motion is to and fro, that is D2. So there you have to use D2. So in this mechanism, see here, tau 1 is equal to d by dt or dou L by dou Q1. Instead of Q1, you have to use theta 1 if it is a revolute joint. You take D1, D or D1 or D2, depending upon you are naming D1 or D2 or D, that D you have to take instead of Q if the joint is prismatic. That is the only difference. But in this mechanism, both are theta 1, theta 2. So you have to find out tau 1 is equal to d by dt or dou L by d. Tau 2 is equal to d by d dl by d theta 2, like that. But in the next equation, tau 1 will be same and tau 2 will be d by dt or dou L by dou d2, because here you have prismatic d2. Here theta 1 only, here d2. That is the difference. That is Q. Clear?
Okay, sir. We have another question from Dr. Srikant. Any recommendation on good books used?
See, there are very good books. One is, if it's for starting, those you are new in this area, you have to use Robotics and Control by Saeed B. Niku. Saeed, S-A-E-E-D, Saeed B. Niku. That's a very good book for the beginners. And that's Prentice Hall publication. And you can use for getting more problems. There are some mistakes in the printing and all, but standard is not much, but you can use that book for Nagarat. So Robotics by Nagarat. And see, you can use Robotics by Craig. Robotics and Control by Craig. Craig is another good book, but Craig is little bit, maybe if you're having some basic idea, you can go for that. And Robotics by Vidyasagar. Robotics and Control by Vidyasagar is another book. And Robotics related Schilling. Dr. Schilling is very good book. Author Schilling. So Schilling, Said B. Niku, Mittal is another book. That is also basic book. Mittal and Nagarat. That is, but there are some mistakes, printing mistakes in that. You have to, but you will get more problems in Mittal. Vidyasagar, Mittal, Said B. Niku, all Robotics and Control application, etc. Then these are the 3 books. And higher level, if you're going, Craig is a very good book. Craig, that's a good book.
Thank you.
And another, my email ID is apsudhir@natc.ac.in. I think Akila can share this, my email ID, to the audience.
Sir.
Okay.
Yes, sir.
Okay. If you have any queries or any help you want, you can mail me.
So one more question. For 6 degrees of freedom, which method is better?
6 degrees of freedom. See, the Lagrangian method you can use, because there are some methodology to formulation. You can use Lagrangian model. Either Lagrangian or Newton-Euler formulation, both are useful. But Lagrangian method, I have explained here. So you try to use Lagrangian, but some methodology is there. That methodology you have to follow. Because trace method, it's a trace method. If you're having any degrees of freedom, you can go for Lagrangian, but there is a algorithm to write the program. That's all. Methodology is same. Lagrangian is okay. You can use Lagrangian also. But I think by hand, if you are writing the mathematical model and all, it's very difficult. So that's why I told you 2-3 degrees of freedom you can write by hand. But if you're writing the program and all, there's some algorithm to use Lagrangian. Some people are using Lagrangian, researchers are using Lagrangian. If you're having more than 6 or 7 or like that, Newton-Euler formulation will be easy to program. In my case, 12 degrees of freedom, I have used Newton-Euler formulation. So Lagrangian is difficult. But 8 degrees of freedom planar robot, I used Lagrangian. Okay. So by practice, you will get idea. You are doing that, you yourself will get idea. Okay, this, why can't we go for this? if you're having external effects, for example, if you're having external effects on the end effector, you try to go for Newton-Euler. Lagrange you cannot use. External effects on end effector. Suppose you have an end effector, you are applying some force externally. That force also can take in account in the Newton-Euler formulation, but Lagrange you cannot use that. But you have to go for assumptions for that. Then you can incorporate. Okay. Are you clear?
Yes, sir. And I've also shared your email ID to everyone.
Okay. Okay.
So any more questions?
I think all of the participants are tired. They started by 9:30, and now see that also mathematics after 12. So there will be find a difficulty in understanding those, especially teachers. Teachers cannot sit much, right?
No,
Okay,
sir.
Akila.
I guess there are no more questions. We have only thank you messages that are coming in the chat box.
Okay, okay. So
So,
I think
on behalf of yes, sir. On behalf of the
Akila will stop
participants,
now then.
yes, sir.
Ah,
I would like to thank you from the bottom of my heart, sir. It was really a wonderful and informative session, sir.
thank you, Akila, and all the participants. You don't stop here. I think this will try to give some idea and try to do something in this area. So
Yes,
that will
sir.
be helpful for the students, and students will be motivated to do further. Okay.
I would
Okay,
like
all
to
the best.
inform the participants that the next session on sensors and actuators would be at 2 p.m. So please
Okay.
log in by 1:50 p.m.
Okay, thank you all. Bye.
Thank you, sir. Thank you so much.